Hello! Do you like math and physics? Do you like chill communities for discussing math and physics? Then join my epic new Discord community, Wizardheim. Because I couldn't come up with a better name. Because physics is wizardry, and wizardry is cool. Also, do you like losing money? How about losing money while I earn it? Then check out my new Patreon, where the only perks are knowing that you're cool. Both the Discord link and the Patreon link will be in the description.
Spinors are often seen as the most confusing subject within theoretical physics. However, I'd argue this is largely due to the vast amount of conventions used without mention. That is, there are many conventions for representing spinors, and most folk, including teachers, don't mention which convention they are using. This actually frustrated me so much that I wrote an article on it. And then I became frustrated again, so I wrote another article. But honestly, there are so many conventions and there's so much information on this subject that I think I could very well write a few more articles on this in time. My initial frustration came from reading two books with differing conventions. Then I went to Wikipedia and other sources to cross-check the conventions and only found more goddamn conventions. So I did the next natural step. I created my own convention and showed how it relates to the others. What is my convention? Well, I honestly don't want to call it my convention since I didn't originally discover it. However, I do think I built on the original convention a good amount. So instead I will call it the natural convention. I call it this because it arises naturally in the geometric algebra of three-dimensional space, which I and other physicists call the algebra of physical space. For a somewhat notationally outdated crash course in this algebra, please refer to my series Special Relativity in 3D Geometric Algebra. Moreover, I call it natural because operations in the convention correspond to natural geometric operations in the algebra. Also, as we'll see, any general element of the APS actually is naturally a sum of two spinors. Before continuing, if you end up liking this video, please make sure to leave a like and subscribe. If you want to discuss ideas in this video, or just participate in my community, make sure to check out my Discord in the description. And if you really want to show your support, a small donation via Patreon goes a long way. To keep this video somewhat self-contained, I will assume you viewers have a basic understanding of geometric algebra. Even if you don't already, I bet that you'll find this approach interesting enough to learn the basics and then return to this video in order to fully understand it. The video will be divided into the following sections: the Pauli representation of the APS, minimal left ideals, the natural convention for Weyl spinors, and main differences in conventions for Weyl spinors. I want to stress that this video is not for understanding the interpretation of Weyl spinors. In all honesty, that topic is deserving of its own video. This video will be purely about the mathematics, so how Weyl spinors are defined algebraically and how they behave algebraically. Now, without further ado, let's begin. The APS has 8 basis elements, 1 scalar, 3 orthonormal vectors, 3 orthonormal bivectors, and 1 pseudoscalar, also called a trivector. Notice that the bivectors are just the product of 2 basis vectors, and the trivector is the product of all 3 basis vectors. Also, it should be noted that the vectors square to +1. Now, the unit pseudoscalar squares to -1 and commutes with all elements of the algebra, so it is equivalent to the imaginary unit. As such, it is labeled I. This allows us to rewrite the bivectors as imaginary vectors. Whether you want to think of them as imaginary or not is a matter of personal preference. Personally, I view imaginary vectors and bivectors as the same thing in the APS, so I don't think it matters much. However, writing bivectors as imaginary vectors will be helpful in this video. A general element of the APS will then be a linear combination of all these basis elements. We can rewrite this in 3 different forms, but I will only present 2 for now. The first is the grade decomposition, where G is grouped into scalar, vector, bivector, and pseudoscalar components. The second is complex paravector form, where G is grouped into a complex scalar plus a complex vector. The grade decomposition of a general element is incredibly useful because there are 3 conjugation operations in geometric algebra, and each one manifests itself clearly through grade decomposition. The first is called grade involution, or parity conjugation, and it negates odd-graded elements. That is, it negates vectors and pseudoscalars, while it leaves scalars and bivectors the same. Specifically in the APS, it can also be called parity conjugation because it actually performs the parity conjugation seen in quantum physics. That is, it negates position in space, but not in time. The second is called reversion, or Hermitian conjugation, and it negates bivectors and trivectors. It's called reversion because it actually reverses the product order, and it negates bivectors and trivectors since by anti-commutativity, they are equal to the negative of their reverse. Specifically in the APS, it can also be called Hermitian conjugation because, as we shall see, when we look at the Pauli matrix representation of the APS, the reverse of a general element corresponds to the Hermitian conjugate of its matrix representation. The third and final conjugation is called Clifford conjugation or adjugate conjugation, and it is the composition of both grade involution and reversion. Thus, vectors and bivectors are negated, while scalars and pseudoscalars are left the same. For those of you familiar with linear algebra, you realize that any element G times its Clifford conjugate will then return the determinant. Okay, we've now covered the basics of the APS, so let's introduce the Pauli representation. I denote represented by with 3 lines since it means equivalent to, and my personal belief is that although representations are not unique, each one is equivalent to what it represents. The unit scalar, 1, is represented by the 2 by 2 identity matrix. The basis vectors are represented by the Pauli matrices, which is why they were labeled with sigma in the first place. The bivectors are represented by the imaginary unit times the Pauli matrices, and the pseudoscalar is represented by the imaginary unit times the identity matrix. Let's now take a look at the conjugation operations in the context of the Pauli representations. I will not be proving what they are, just presenting their forms. If you're curious, I encourage you to attempt the proof yourself. Here I've included the matrix representing G and all its conjugates. If you're interested in seeing the differences, I recommend pausing the video. Notice that the entries for each matrix element are just complex numbers. Having presented the Pauli representation, let's move to discussing minimal left ideals. Some of you may have seen my last video, which was on a new and simple geometric interpretation of Pauli spinors. In it, I gave this definition of an ideal. For the next few minutes, I will pretty much copy what I said in this last video and say it here. A left ideal is a subset of an algebra that is closed under multiplication and absorbs other elements of the algebra through leftwise multiplication. Practically speaking, this means that we limit ourselves to only multiplying things on the left, and no matter what we multiply by, we stay in the ideal. We are talking about minimal left ideals, which just means that there are no sub-ideals. The best way to motivate this concept is by using the Pauli representation. Here we have some element G times another element. The result of this multiplication is that only the left column remains containing elements. Suppose we then multiply this object by another general element H. Then we will still stay in the left column. We have therefore found an ideal. We won't bother with the proof, but this ideal also happens to be minimal. An interesting thing is that there's also another minimal left ideal in the right column that exists fully independently from the other. That is, there are 2 inequivalent minimal left ideals in the APS. Technically, there are infinite based off of your choice of basis, but once you choose one, there are only 2 inequivalent minimal left ideals. Looking at the 2 generators, which are more accurately called projectors or idempotents, we can see that they add to the identity matrix. Mathematically, we say these projectors partition unity. That is, they split the number 1 into 2 idempotent projectors. The one projector to the left-hand column is labeled F+, while the projector corresponding to the right-hand column is labeled F-. Both are idempotent, meaning they square to themselves. They partition unity because they add to 1. They are also mutually annihilating, so when you multiply f plus by f minus, you get 0. But what are these projectors in the APS? We can clearly see their properties in the Pauli representation, and then carry them over to the APS as we've done here. But what explicitly are the projectors? Let us derive them from the Pauli representation, and then once again carry over our result to the APS. We can factor the 1 and 0 respectively in the top left and bottom right corners. After factoring them, we find they are just the number 1 and the z-direction Pauli matrix. Therefore, the projector f+, which generates a minimal left ideal, is the quantity 1/2 1 plus sigma z. We could also solve for f- in the same way, but instead we'll use the fact that these projectors partition unity. It turns out that the projector f- is just the grade involution, or parity conjugation, of f+. Furthermore, it seems that f plus minus is equal to 1/2 1 plus or minus sigma z. Here is a summary of the important identities that we will use a lot when I present the natural convention for Weyl spinors. I will denote these independent minimal left ideals as I plus and I minus. Notice that a general element is itself times the number 1. Because the projectors added together equal 1, the element G is split into two inequivalent ideals. The portion multiplied by f plus is a left Weyl spinor, and the portion multiplied by f minus is a right Weyl spinor. Therefore, any object in the APS is a sum of a left and right Weyl spinor. I can almost guarantee that this is not how Weyl spinors are taught anywhere, so I'm sure this seems very foreign. But let me continue, and I'll show you how natural this algebra of Weyl spinors is. In quantum mechanics, or technically just in general, it's known that parity conjugation swaps handedness. That is, left Weyl spinors become right Weyl spinors, and right Weyl spinors become left Weyl spinors. This is exactly what happens when a Weyl spinor undergoes grade involution. This is why I called it parity conjugation earlier, because grade involution swaps left and right Weyl spinors. Hopefully you can see why I called this the natural representation. All elements of the APS can be naturally decomposed into the sum of a left and right Weyl spinor, and there is a conjugation that naturally corresponds to parity. Another reason that is more of a theme than any one fact is that all mathematics needed to describe Weyl spinors are within the APS naturally. Weyl spinors are traditionally presented as column vectors, and there is an obvious correspondence between the single columns of the Pauli representations and the column vectors. However, a question arises from this. Namely, do the coefficients here correspond to the coefficients of the traditional approaches? In other words, is it true that each coefficient corresponds to spin up or spin down in the column vector? It turns out this is a question with a lot of mathematical background and build-up, so I will present the tools without a derivation to answer this. There are right and left Weyl spinors which emerge naturally from the APS. They are elements of both of these inequivalent left ideals. We can switch between these two ideals via parity conjugation. What I didn't mention before is that there are two other ideals which are mathematically dual to the original ideals. These new ideals are minimal right ideals rather than the original minimal left ideals that we've been working with. We can also switch between these two ideals via a duality operation, which is the x basis vector times the Clifford conjugate of the spinor. Notice that the duality operation's inverse is not itself. It is still possible to switch between these two dual ideals via negative parity. I hope the simplicity and beauty of this diagram is appreciated. When I first drew it, my mind was blown. I just couldn't believe that the relationship between Weyl spinors was so simple, and more so that every single aspect needed to describe it was naturally within one single algebra. But I can hear you asking me, why do we need dual spinors? And how will this show what coefficients relate to each other? The answer to both lies in the spinor product. Here it is without derivation. However, the derivation is quite trivial in this case because it is just the product between a dual left Weyl spinor and a left Weyl spinor. The same product exists for right Weyl spinors too. However, for the rest of this video, we will focus on the spinor products for left Weyl spinors. To get a better understanding of spinors, dual spinors, and the spinor product, Let's calculate such a product. First, we compute the dual left Weyl spinor. Then, all that's left to do is compute the final result. There is a thing in spinor mechanics that the spinor product of a Weyl spinor with its dual must be 0. Let's check to see if our spinor product satisfies this condition. Indeed it does. Now that we know for sure that this is the spinor product for left Weyl spinors, we will show how the coefficients from the natural convention are related to the traditional column vector. To begin, we realize that the projector F plus represents spin up. This means that the alpha 1 coefficient corresponds to the spin up coefficient. I won't demonstrate this explicitly here, but I did present it in my Pauli spinor video, so I recommend checking that out if you're curious. This immediately implies that the alpha 2 coefficient corresponds to the spin down coefficient. But what does it mean about the right Weyl spinor coefficients? To check this, we'll need to turn a right Weyl spinor into a left Weyl spinor via parity conjugation, and then we'll need to turn that spinor into a dual left Weyl spinor. However, after computing the product, we'll unfortunately have to compare it with an outside source to determine the relationship. I apologize for the wall of algebra that this video has been so far. The traditional product between a left and right Weyl spinor has this form. Let's now compute this product within the natural convention and compare. First, we need to turn this right Weyl spinor into a left Weyl spinor via parity conjugation. Second, we turn this left Weyl spinor into a dual left Weyl spinor. Lastly, we compute the result. Comparing the two, it's easy to see that the first coefficient actually corresponds to negative spin down, and the second coefficient corresponds to spin up. Here are some arrows to show the correspondence a little more clearly. So we can see that any general element of the APS can be viewed as the sum of a left Weyl spinor and a right Weyl spinor. For the left spinor, the top coefficient is spin up and the bottom is spin down. For the right spinor, the top coefficient is negative spin down and the bottom is spin up. Let's summarize what we've done so far. We first introduced left and right Weyl spinors as elements of inequivalent minimal left ideals. We saw that it was possible to move one spinor to the opposing ideal via parity conjugation. Moreover, we can also move between Weyl spinors and dual Weyl spinors. Everything is summarized in this graph. We then introduced the spinor product. The spinor product of a spinor with itself was seen to be 0. Using this product, we found that a general element of the APS can be viewed as the sum of a left Weyl spinor and a right Weyl spinor. For the left spinor, the top coefficient was spin up and the bottom was spin down. For the right spinor, the top coefficient was negative spin down and the bottom was spin up. There are basically two conventions for Weyl spinors. Technically, there are many more than two, but there are only two mathematically different conventions. There may be more, but from everything that I've read, which was a lot, I only found two. For this reason, I call them formalisms rather than conventions. Different notation within each formalism is then a convention. For the first, I use the term traditional formalism. It deals with spinors as purely row and column vectors which interact via a spinor metric. As matrices are the basis of the formalism, operations like transposes are allowed. In the natural convention, which I've presented thus far, there are no algebraic operations that correspond to transposes, so it's not a traditional formalism. For the second, I use the term natural formalism. Another good name is algebraic formalism, because all conventions that are a part of this formalism are natural results of geometric algebra. I prefer the adjective natural, though, precisely because this formalism is a natural result of geometric algebra. Not only this, but rather than saying we're looking at column or row spinors, we're saying that we're looking at different minimal ideals of an algebra. Moreover, the way these ideals are related makes the spinor metric an implicit truth. This means you'll never have to actively pay attention to using a spinor metric so long as you follow the graph of relations between ideals. For emphasis, here's that graph of relationships between ideals in the APS. And here's the graph of relationships in the traditional matrix formalism. It's quite different from the natural formalism, so hopefully it's obvious how they are not mathematically identical. It's also well known that the APS can describe classical physics, relativistic physics, and the Dirac equation. I actually made a video demonstrating this. So the benefits of using the natural formalism outweigh the traditional matrix formalism significantly, in my opinion, particularly considering how the natural formalism means using the APS, and using the APS means you can describe most areas of physics. That's it for this video. A lot of work went into developing this formalism fully and finding out the best way to present it. If you liked it, then please make sure to leave a like and subscribe. If you want to discuss ideas in this video or just participate in my community, make sure to check out my Discord in the description. If you really want to show your support, a small donation via Patreon goes a long way. Anyway, see ya.